For our next talk, we have Thomas. Thomas is an assistant professor at EPFL and has been working at the intersection of hardware design languages, computer architecture, and programming languages. And if you know anything about hardware, you know it's like massively, massively concurrent. And this talk has a very enticing title about how you can sort of get a handle on all of that concurrency and do all of your cool verification tasks. Thomas, please take it away.
Thank you. Let me put the timer. Okay, thanks for the introduction, Ratchet. So I will present some work that I did while I was still a grad student a few years ago, and it's a work with my co-authors, Elvis Liu, and my advisors, Adam Chlipala and Arvind. So as Ratchet said, I've been doing architecture and verification, hardware verification for a while, and sometimes I have the syndrome of grass is greener on the other side. And when I look at software verification, one of the things that is very standard that I like very much is the modularity that is at the core of many approach. One of the key things is like you can have a class that can be verified against a specification that assigns a precondition and post-conditions to each method. Then the methods are proven each in isolation. And then a client of the code can verify their own functionality without ever needing to look at the implementation. You know, on the hardware side, the story is a bit different. The abstraction that we work with is an abstraction of the actual circuit. It's called the register transfer level abstractions, where you have a state, typically a bunch of registers that are updated every so-called clock cycle with a Boolean function. And the good thing about that is that it's such a low-level representation that you don't need to get married to a new programming language to do verification. All the verification flow works at a very low level. And it works with Boolean equivalence, and it allows you to do bounded model checking. The bad thing is that there is no notion of function calls, object, and method at that granularity, and so there is no good notion of modularity, and verification doesn't scale very high. Very useful, but doesn't scale for full functional correctness. So our goal for a few years has been to try to verify functional correctness of interesting computer architecture designs in an ITP. And to do that, the first thing that we wanted to do was to recover software-like modularity in hardware design languages. And so to tell you that, the first thing we are going to do is to not write hardware languages. We are going to write in a slightly higher level of abstraction called Bluespec. So I need to tell you a tiny bit about Bluespec before I tell you about what we did to Bluespec to make it more amenable to verification. So in the Bluespec system Verilog methodology, you know, as an architect, you often draw these kind of diagrams where you want to design a pipeline, and you know you have some function f, some function g, and you would like to write a hardware that does that. And in Bluespec, the way you do that is you don't write a state update function on registers. You just describe that machines as a bunch of objects, which are the submodules, the three queues, in, mid, out. And you write the methods that your new module has. There's an enqueue method here, where you can push stuff in the box, and a dequeue and a result method here. And the methods are basically things that are changing the state of the module, changing the hardware state, or observing the state. And there are rules that are, once you have pushed something to the machine, it goes on its own mind, and you can think of it in automaton term as epsilon transitions. They keep going in the background, non-deterministically, so it might pull from the in queue, push into the mid queue, pull from the mid queue, pull out. Submodules are recursively themselves of that form, method rules per submodules. And you bottom out at modules which are just registers, which have just read and write methods, and BRAMs and a few other primitives. So the Bluespec system Verilog methodology is you describe your hardware design in that lingua, describing submodules, rules, and methods, and then you use a compiler to derive the state update functions. And you know, a few years ago, we had a PLDI paper to study the proof of correctness of such a compilation scheme, but we had not looked at, and there's been prior work looking at verifying not things here, but verifying things there on the left-hand side. And that's what the rest of this talk is going to be about. So it already looks like I have given you a software abstractions, because they are, you know, objects like submodules, and you have methods, so it looks like we have software abstraction. Well, there's a little plot twist here. The base modules that we have, a register which has a write and a read primitives. If I have a register that holds 42, and I write one of those rules that tries to write 1 to the module and then displays a value, actually it doesn't display 1. It displays the old value in the registers. And that's coming from the fact that Bluespec being a hardware language, at the end of the day, it's just wires connecting to submodules. And the read always happens before the write in a clock cycle for registers. So the semicolon is, you can think of it as parallel composition instead of sequential composition. So when you describe a rule, you are simultaneously doing all the actions that you are calling onto the submodules. So here, read after before write happens before write. this very simple issue creates a problem when you try to characterize a module in isolation. Let's look at this module. And this module has two methods, write A and write B, two methods to update, and two methods to read A and read B. And intuitively, there are just two registers hidden inside. If I were to write a client that try to, oops, sorry, there's a typo, it's not set A, it's write A, and it's not get B, it's read B. If I read B, put it in A, and read A, put it in B, then if I try to characterize what this thing is doing, you can think about it in your head, then it's not going to be a state update that is explainable in terms of sequence of calls to those methods. If I had 0, 1 in A and B, after I do that thing, I'm going to get 1, 0. I would have swapped the two values, and I will never be able to explain that behavior in terms of a sequential behavior. It's not a sequential behavior. So this is a fairly annoying problem. And this led us, this led previous work, Adam and Arvind at work in 2015, Cami, that, so the problems that we always try to do is proving a refinement. You have a complex implementation with an interface, you have a simple specification of the same interface, and you want to say that all the behaviors on the left-hand side are behaviors of the right-hand side. But because of this concurrency issue, all the behaviors, including not just sequence of method calls, but sequence of sets of method calls. You have to consider that every time I could try to simultaneously call enqueue and dequeue, enqueue and result, result and dequeue, and so you have a power set of things to consider. So if you wanted to prove an equivalence between modules, you needed to basically consider an exponential number of cases, and that in all those cases, your complex implementation was indeed producing a behavior that was in your simple spec. So you can't characterize, you could not characterize a module one method at a time. So this was a little limiting because it made refinement harder to use. And it was not really necessary, so we did this very childish step of saying, do we really need to be able to call multiple action methods simultaneously? So normally in the previous work, every method was considered the same kind of methods. Methods that change the state and methods that read the state were all smashed into one family of methods. And we did two childish steps. We started by saying, let's separate methods that purely update the state from methods that are observing the state, called value methods. And then let's simply forbid calls that calls two action methods of the same module in the same rule. When you do that, you're morally restricting the language to multiple readers, single writers, where concurrency and management is much simpler to handle, and Bluespec can basically do that, and then you can explain every behavior in terms of a sequence of behaviors. So we did that. I will tell you in a minute why that doesn't hurt expressivity. But what it gives us to give this restriction is that then we can characterize a module in Bluespec as a very simple transition systems and with a very simple notion of equivalence between transition systems. So the notion of transition system will be denoted by the type of the state will be the product of the submodule states. The rules are simply going to be relations on states. The methods are going to be of two kinds, relations and action method and relation and value methods, which are state cross argument cross new state and state cross argument cross new value return. And that's basically just a mass description of any Bluespec module. Very convenient because once we have that, so we can model partial transitions and non-functional relations for non-determinism. But more importantly, we are on the highway in terms of theory. We can reuse very well-known theory of weak simulations to be able to study how one system is implementing another system. And I'm going to go quick on the details there. You can read the paper for more. But the key thing is that it gives us a nice substitution principle that is exactly what we were looking for. That is, if you can prove that a module implementation refines a module specification in the sense of weak simulation, then any usage of that module will refine any usage of the specification. And that's exactly the idea of saying for verification purpose, we never manipulate the implementation. We always manipulate replacing the implementation by the specification to study the bigger module. So we typically use case is like, let's say that in your hardware design, you have a circular buffer implemented with enqueue pointer, dequeue pointers rotating around. You don't want to do verification on that. You have a lot of symmetry of equivalence. It's very annoying. The first thing you do is you prove that this refines a list-based, non-synthesizable specification. And then when you do your verification of your module using that list, you are using only the list-based version. And you have a theorem proven in Rock to do that. So now let's use all that theory. Actually, before we use all that theory, let's assess a little bit the restrictions on can we still write useful Bluespec design with that restrictions. We did a little static analysis to the Bluespec compiler to basically assess is it the case that existing code was violating those assumptions or not. And we fed it about, I think, 300,000 lines of code. And we found a few violations. I don't want to get too much into detail. I can tell you later if you're interested. By the way, it's a good way to find places where students 15 years ago wrote hack, hack, hack in their code. So now let's go to actually using this nice software-like refinement view of the world. So our use case is going to be a little processor. So we would like to study sort of a pipeline processor. And the theorem we would like to get is to say, well, if we were to plug this processor to like a terminal, which is talking to the processor, to the machine through an MMIO line, exchanging bytes on an MMIO line, then we would like to get the theorem that any interactions between the keyboard and the screen in MMIO to the pipeline processor are traces that could have happened in the simple specification processor. Where on the left-hand side, the process is going to be slightly more sophisticated, that on the right-hand side, it just executes instructions one by one. And in this case, instruction and data memory are basically part of the system, but they are out of the processor. And the whole goal will be able to prove the processor independently of the memory. So the processor, the family that we studied is fairly simple and also complicated in one sense. So it's fairly simple because it's just a 4-stage pipeline. But it doesn't mean that it has only 4 instructions in flight. Actually, it has arbitrarily many instructions in flight because the size of the queues are arbitrarily sized. And it was very important to us to do that because we were especially interested in looking at verification in the context where you have speculative loads, where you have multiple outstanding data load or instruction load. Because a lot of complex things we're going to see are happening because of that. So the straw man would be to say, well, I need to prove that thing. So that's easy. I'm going to use a refinement theorem to just prove that thing. I'm going to prove that the implementation processor is a refinement of the specification processor, and then I will have won because I've used my refinement theorem to lift it up. And that would be sort of like, the natural modular verification strategy, except it doesn't work. Why it doesn't work? Because the theorem is not true. Why is the theorem not true? Because the pipeline processor has actually many, many, many more behaviors than the simple specification that emits the load and the stores one by one. Think of it like this. In the implementation, my processor might back-to-back send 2 instruction requests back-to-back before it even gets a response. It speculates 2 instruction requests. On the right-hand side, this will never happen because you only emit the next request once you have got the response for the instruction and once you have finished the full execution. So it's not that the theorem is hard to prove, it's that the theorem is false. This behavior does not exist in the processor specification. So we were very excited because we realized that this simple problem, we didn't even have a spec for it. We don't have a valid spec just for a processor. We have a valid spec for the full system, which happened to be made of a processor and a memory, but we don't have a spec of just the processor. And we are not talking about multi-core weak memory model, this kind of business here, right? We are really talking about single core, but doing the study of the processor in isolation of its memory. So to solve this problem, basically we are taking an opinionated stand, right? We are saying we need to tell you, architects, what are all the possible things that all the possible optimizations that your processor should ever be able to do. How many load what kind of load you should be able to issue, the reordering between load and stores. That's what such a specification should say. So it sounded like a hard thing to come up with. How do we write a spec that can cover any possible processor implementation in the future, or at least all specific processor implementation, which was just pipelined? And the idea is very simple. The idea is to say we are going to stitch together this sequential 4-cycle machine. We're going to stitch it with 2 non-deterministic load machines. Instead of the processor sending its request directly to memory, it's going to send it to what we call a load buffer. And that load buffer is not just buffering the load, it's also emitting random loads to random address at any point in time, non-deterministically. So the way we think of this is basically we say the spec of a processor is not just the spec of a simple ISA machine that goes one by one. It's that plus just you randomly add a bunch of loads anywhere, any address. Because architecturally speaking, loads don't matter. Data speculation techniques can be very wild. You would never know where they will send a load, when they will send a load. So conservatively, just say you could send a load anytime, and that's going to be your new spec. And we will just, there's a little bit more things on store, but I won't elaborate on that much more. So why is it the case that the generalization is valid? Well, architecturally, it's kind of obvious, right? There is this saying that loads don't matter. only store matters, but is that intuition formalizable? And yes, it is formalizable, because we need to be careful. We can't just change our specification. I just changed the rules of the game. I told you the old spec didn't work, let's just replace it with a new spec. But if my new spec was I could also send random stores, then I would have just said nonsense. So the theorem that you get is the following. So on the first hand, you're going to prove that your processor refined its generalized specification, which is basically simple processor plus random loads. You do that, then you apply the refinement theorem, you get that theorem below, and then you need to prove another theorem, which is the correctness of the generalized specification. That is, from the perspective of the outside world, from the MMIO request perspective, these extra loads you sent did not disturb the system behavior, the system level behaviors. And that's a second proof that you need to do, and it's actually not very hard because loads actually don't matter. So we verified a few more designs. Elvis wrote a network switch, a programmable network switch with a nice specification, which is deeper than the processor. And then we proven a crossbar as well, and a processor, a family of processors. All of that, you can find more details in the paper. So what I wanted to tell you today was two simple things. First, we can characterize hardware modules one method at a time in the software world. But when you get that, you're not done, because you are facing the standard problems that actually writing modular specification is hard. And you need to find a way to generalize the different components you want and to say all the acceptable behaviors that those subcomponents should have for your full system behaviors to be true. And in the case of processor and memory, we are quite excited because we are getting into a way to decouple the memory from the processor. It's actually sort of bringing memory model questions even in the single core core setup. There is more, I think in my dissertation, maybe not in the paper, on that, but it's very interesting. It gives us a way to start reasoning about weak memory model in a more operational way. And thank you.
Please raise your hand if you have questions, and the volunteers will bring the mic to you. Just to get us started, so there's this very interesting insight that sort of the simple sequential specification of a processor is not actually the right one, and you have to add some amount of non-determinism to sort of make it general enough to actually prove properties against it. I have two related questions. One is that, are there other places you think you would need to add non-determinism to express the kinds of microarchitectural optimizations people are sort of thinking about? And two, oftentimes people want to test the specifications, which are higher level, and sort of think about how to compose them in a broader system. Now that you have so much non-determinism and so many traces that sort of might look foreign, what do you do with that?
Yes, so both are interesting questions. So the first one, about other places where you need non-determinism. Yes, so actually the first example that we had was an example where you have so we used to always study GCD machines because those are very simple machines but are very interesting. So little hardware blocks that can compute GCD between two numbers. And you would like the spec of that things to be just some things that just take an input, produce a GCD and produce the output. And if you have an implementation that does a lot of reordering and that does a lot of things, then you do need a step of generalization to make it work. And it's actually quite easy to do, to write this generalization. So I think there might be something about that in the paper or in my dissertation of a simpler case of generalization, which is exactly this idea of sometimes you might need to add a queue somewhere, sometimes you need to add a little out-of-order completion buffer somewhere. Logical, it's not a physical thing in your spec, but that works. Then in the processor case, I think, yes, the answer, actually the things that I outlined, we turn out that you can sort of draw a bridge between whatever you write here and whatever is your weak memory model. So if you're abiding by a weak memory model, one given weak memory model, then there is basically one kind of wrappers that you need to write around it. And so if you have a different weak memory model, you will have a different kind of wrapper. So you don't generalize the same way depending on your weak memory model. And that's a difficult question that we have not finished answering yet. Outside of memory, I don't know. So we have only looked really seriously at the boundary between processor and memory. I've looked a little bit at the boundaries, at other boundaries, but they are more inside the processor, and there we didn't need generalizations. So it's kind of, it really depends. And then your second question, I forgot what it was about. It was testing. Yes, testing. Problem was non-determinism. Yes, non-deterministic testing. Yes, it's hard, and we don't know how to do it.
Nathan Beckman, CMU. Do I understand correctly that you constrain that the stores have to come out of the processor to the memory in the order, the same exact order of the sequential?
So that's, I explicitly say that I didn't say anything about it, right? Yeah. So you're asking me to tell more about it. So in the implementation of the processor in the code that is in the artifact, yes. Then we slightly tweaked it, because obviously some person was not happy with that. We basically glued together a store buffer and a load buffer. And in that situation, then you can have reordering in your store buffer. So you don't emit the store directly. You let it go through the store load buffer. So if you remember, they did I2 paper a few years ago at ISCA, and we are reusing some of those ideas there.
Thanks.
Let's tag the speaker one more time.